Hi everyone, my name is Thant, and today I'm going to present my coursework project on image classification using a neural network. For this project, I designed and implemented a convolutional neural network to classify images from the CNFA or Thant dataset. The goal was to build a machine learning model that could automatically recognize 10 categories of objects such as airplanes, cars, birds, and dogs. Throughout this presentation, I will explain my code step by step from setting up the environment to making real-time predictions and show how I evaluate and improve my model. So, the first step, I imported all the required Python libraries. These included TensorFlow and Keras for building the neural network, NumPy and Pandas for data manipulation, and Matplotlib and Seaborn for visualizing results. I also checked my environment configuration, mainly to confirm that the GPU was available, because training deep learning models on CPU is much slower. Next, I loaded the CNFA or Thant dataset, which is conveniently included in Keras. It contains 60,000 images, color images, each 32 by 32 pixels, evenly divided into 10 different classes. I first printed the shape of the training and testing set to verify the data structure, and then display one sample image from each class. This visual check helped me understand what the model will learn. For example, how similar cats and dogs look at this resolution, low resolution, and how airplanes and ships have distinct shapes. I also confirmed that the dataset was balanced, meaning each class had the same number of images. So before training, I performed several preprocessing steps to prepare the data. First, I normalized the pixel values from 0 255 down to 0 1 by dividing by 255. This helps the neural network train more efficiently because smaller values keep gradient stable during learning. Second, I one-hot encoded the labels. Since there are 10 categories, each label was converted into a vector of length 10 with 1 at the correct class index. Finally, I split the training data into training and validation subsets so I could monitor how well the model generalized. In step 4, I designed a convolutional neural network architecture. The network has 3 main convolutional blocks that progressively extract higher level features from the images. The first block uses 32 filters to detect simple edges and textures. The second block with 64 filters captures more complex shapes. The third block with 128 filters learns object level features. Finally, I compiled the model using the Adam optimizer, which is optimization algorithm, and categorical cross entropy loss with accuracy as the evaluation metric. For training, I use a batch size of 64 and run up to 50 epoch. To make training efficient and stable, I implemented 3 callbacks. The first one is model checkpoint, which automatically saves the best model based on validation accuracy. The second one is early stopping, which stops training when performance stops improving, so it can prevent overfitting. And the third one is reduce alert on plateau, which lowers the learning rate when progress slows, helping the model converge better. The training was performed on the augmented data generator, which feeds new random image transformations each epoch. After training, the model achieved around 95% training accuracy and 85% validation accuracy, which shows a good balance between learning and generalization. Once training was complete, I evaluate the safe best model on the test dataset. The final test accuracy was approximately 84 to 86%, which is quite good for a custom CNN trained from scratch on CNFER10. To analyze the performance in more depth, I generate several plots and reports. The accuracy and loss curve over epoch show that the model converges smoothly. A confusion matrix visualized when the model made mistakes. For instance, it sometimes confused cats and dogs, which looked similar at small resolutions. A classification report provided precision, recall, and F1 score for each class. I also display exam predictions with their true labels and confidence scores. These visualizations make it easy to understand the model's strengths and weaknesses and to demonstrate its effectiveness clearly. To make the project interactive, I implemented a feature that allows users to upload their own image directly into the notebook. Once an image is selected, the code automatically resizes and normalizes it to match the training data. Run it through the CNN and then display the top 3 predicted classes with their confidence level. For example, if the uploaded image is a dog, the model might output dog like 93%, followed by cat and deer as less likely alternatives. To summarize, I successfully developed a complete image classification system using a convolutional neural network, starting from dataset exploration through preprocessing, model design, training, and evaluation. Each step contributes to building a reliable and explainable model. The project improved my understanding of deep learning concepts such as feature expression, overfitting, control, and model evaluation.